Last time we looked at how a neural network works: an input layer, one hidden layer, and an output. That single hidden layer was enough to combine weighted signals into a decision. But real problems, like separating malware from benign files, are messier than one layer can handle. So what happens when we stack many hidden layers instead of just one? Deep learning is simply this: a neural network with many hidden layers stacked between the input and the output, instead of just one. Each layer takes the previous layer's output and transforms it again, passing a refined signal deeper into the network. Stack enough layers and the network learns far more complex patterns than a shallow one ever could. That's literally where the word deep comes from: depth, not intelligence. Here's why depth is powerful. Each layer learns a different level of abstraction. Feed in raw file bytes, and the first hidden layer picks out tiny local patterns. The next layer combines those into structural features, like suspicious code blocks. A deeper layer combines those into full behavioral signatures. By the time the signal reaches the output, the network isn't looking at bytes anymore. It's recognizing malware families. You might ask, why not just make one hidden layer huge instead of stacking many smaller ones? You could try, but a wide, shallow network has to learn every combination of features directly, needing enormous numbers of neurons. A deep network reuses what earlier layers already learned, building complexity gradually, a far more efficient way to represent complicated patterns. Nothing new mathematically inside a deep network. Every neuron in every layer still does the same job we saw last time: multiply inputs by weights, add a bias, pass it through an activation function. Depth just means repeating that simple operation over and over, layer after layer, refining the representation many times before a final decision. Depth sounds great. So why didn't everyone build deep networks from day one? During training, the network sends an error signal backward through the layers to adjust each one's weights. In very deep networks, that signal can shrink so much by the earliest layers that they barely learn at all. This problem is called the vanishing gradient, and for years it made truly deep networks impractical to train. Deep learning became practical once three things lined up: far more labeled data to train on, far more computing power, mostly GPUs, and better activation functions that kept the gradient signal alive across many layers. Around the early 2010s, these pieces came together, and deep networks started dramatically outperforming older approaches, especially on messy real-world data like images, text, and files. So deep learning is a neural network with many hidden layers, each building on the last to learn increasingly abstract representations of the data. That's the engine behind modern malware classifiers, phishing detectors, and facial recognition systems your security tools may already rely on. Whenever you hear deep learning in a product pitch, you now know exactly what's happening under the hood: layers, stacked deep, learning stage by stage. Next time, we'll zoom into one special kind of deep network built specifically for images and visual patterns: the convolutional neural network, or CNN. Subscribe so you don't miss how it works.